Welcome to 8.2 in Math 31, which is the derivative of exponential functions. And we're going to look at a few different ones as we go through. But to begin with, one of the big changes with exponential functions that we typically do in calculus is that it's pretty rare that we use a base of 2 or 3 or 0.5. We can, and there's nothing wrong with that. But what we're going to use much more often is base e. And it's not something that you've dealt with before. They have the formula for it. They say symbolically the limit as h approaches 0 of e to the h minus 1 divided by h is equal to 1. I've added an additional video within this section to try to explain exactly what e is. And the best, I think, explanation of what e is it's really the base that we use when we have something called continuous exponential growth. And it's one of those things that it doesn't really happen. Like if I had 10 rabbits, that's not continuous exponential growth. There's only, so often the rabbits can be pregnant and so on. But if I had a population of, let's say, 6 billion, because we've reached a number in that population that's so large, using or modeling this as continuous exponential growth does one major thing, and it makes the calculus a heck of a lot easier to do. And we are going to learn how to deal with different bases. But today, we are going to learn how to take the derivative of e to the power of x. And I always kind of chuckle when students see this because they think that it's not really saying anything at all. It says that the derivative with respect to x of e to the x is equal to e to the x. And it kind of looks like we're not doing anything there. But what becomes all the more important is that this is, again, one of those situations where this is as simple as we can write that function. What you are much more likely to run into is the derivative with respect to x of e to the power of some function. And the derivative of this, and it is just using the chain rule with what's above, but what this would be is we would have e to the power of f of x still, but then I would be multiplying by the derivative of the inner, or the function in the exponent in that case. Now this is in your notes as well. I like writing it with function notation because sooner or later we are, and I say sooner or later in this lesson, we're going to run into examples where we have to deal with that kind of more complex exponent. I would recommend that you go watch that video on Euler's number right now. It will help clear up a little bit of the kind of misconception or exactly what that number is. I'm going to be honest, you don't really need a really in-depth understanding of what Euler's number is, but I do believe it helps. It's that difference just writing a lowercase e between understanding that it's actually modeling continuous exponential growth. All right, so without further ado, let's get into some of these problems. So they are just asking us to differentiate. That's finding y prime or take the derivative. This first function is a product rule. The derivative of the first function, which is x squared, is going to be 2x. That's multiplied onto e to the power of x plus the first function. And then here we multiply by the derivative of e to the x, which is e to the x. And we get our function there. Now, sooner or later, you're going to have to clean these up. And for this particular example, what I could do is I could factor out an x times e to the x, and that would leave me with a 2 plus x. And that would be the simplest version of the derivative there. All right, in B, a lot of Euler's number on this page, so I'm going to probably make the mistake more than once. In B, to find y prime, this is that example that I put on the previous page. So right now, this right-hand side is really taking the form of e to the power of f of x. Well, if you look back up, I suppose, if you wrote it down, we're going to say that y prime is still e to the power of f of x. So e to the power of the sine of x is still there. But now what I have to do, I'm going to write it out here, is I have to multiply this by the derivative of the inner function, which for this example is the sine of x, the function inside the exponent. The way that we do that, hopefully you remember your chapter 7 still, the derivative of sine x is cos x, and there's really nothing we can do with that function, but what you will see quite a bit is anything that's multiplied on to that exponent will be written in front, like it's a coefficient. All right, a couple of derivatives, and that's really what most of this section is just taking the derivative, and there'll be a couple questions where we actually apply the derivative, like we have in previous chapters. The really new stuff today is this. The concept, and here, again, I don't really like how they write that, but they say that d over dx of e to the power of u is e to the power of u times, and I'm going to write down here that that's actually du over dx. All right, that's the derivative of the inner function with respect to x. Now, these can start to look a little bit ugly as they get more and more complex, and certainly in this third example that happens, or second example, I guess, part A here. So y prime is going to be equal to, this is a product rule. There are two functions here. I'm just going to put a square bracket around that e to the power of negative 3x. So the first thing I'm going to do is take the derivative of e to the power of negative 3x. And that's e to the power of negative 3x times negative 3, which is the derivative of negative 3x. And that is still multiplied onto the cos of 2x. Now that is, and maybe let me write the product rule up here. So if you have f times g of x, and you're taking the derivative of it, this is equal to f prime of x times g of x plus f of x times g prime of x. What I've just done below is f prime times g of x. And maybe I'm just going to really doctor this one up. I'm going to say that this blue bracket, I'll make that g of x. So this is g of x. I'll make this blue bracket f of x. So this entire piece is f prime of x. So what we need to do next is we're going to add, and I'm going to kind of, hopefully this notation helps and isn't making it uglier to read. I am just going to have f of x. So e to the negative 3x is there. But what I need to do is I need to multiply that, and I'm going to use a bracket. I need to multiply that, and maybe I'll wait to do the curly bracket because we'll figure out g prime first. So the derivative of cos f of x is negative sine f of x. So I'm going to have the negative sine of 2x, but then I have to multiply by the derivative of the inner function, which is 2. And again, to try to match up our notation a little bit, this right here is g prime of x. Now, what I'm going to look for in this next step is any factor that's common to both of these two terms. So I'm going to write, and I'll just do a different color. I should use black at the beginning, but that's okay. Y prime. So I see that both of these functions have e to the negative 3x within them. I say functions there, sorry, both of these terms. And I also notice that both of these terms have a negative. So if I took out a negative e to the negative 3x, which is tough to say for sure, what's going to happen is I'm going to have 3 times the cos of 2x left in my first term, and I'm going to be adding 2 times the sine of 2x in my second term, and that is definitely where I'd stop. That's certainly ugly enough, but even doing this is a pretty big benefit. It sharpens our factoring skills, and sooner or later, namely the next example, you're going to have to be able to factor an exponential derivative. All right, the next example gives us a bit of a point to that. We want to find the absolute max and the absolute min. Now, when we do this, then we might not have an absolute min, and I actually believe this question won't have an absolute min, just because of how that function would look like. What we need to do is we need to find our critical numbers. Critical numbers being when I'll write y prime is equal to 0 or undefined, and then we're going to need to make a sign chart. So hopefully this is something you're pretty comfortable with. You guys rocked chapter 5, so that's usually not an issue. What makes this chapter harder is the derivative of the exponential functions, and sometimes factoring that derivative. So for this question, y prime, it's a product rule again. The derivative of x is 1. I'm going to multiply that by e to the negative x. I'm going to add x, and I'm going to multiply by the derivative of e to the negative x, which is e to the negative x times negative 1. Now, make sure you maybe go back to that last example and see that kind of that product rule at work. Really, really important that we get that derivative right. Otherwise, the rest of this question is really difficult to do. All that I see that we could factor out is I could take out an e to the negative x, which leaves me with 1 minus x. And now I can find my critical numbers. Now, it is difficult to see, but e to the negative x is never negative. And never 0 for that matter. It doesn't change signs. One of the best ways of seeing that, and I want to write it over here, that e to the negative x is basically, and I'm going to put the number in, it's 2.71. It goes on forever, but it's to the power of negative x. Now, what that looks like is it's the exponential function 2.71 to the power of x, which is just exponential growth. But then what's happened? It's been reflected across the y-axis. And I'll draw that reflection in red. So this is my function right here. Taking a look at that red function, it is never 0, it's never negative, and so it doesn't have any contribution to the critical numbers. And I'm going to write just right here that it's always positive, right? That's going to be helpful in our sign chart as well. So my critical number is only found from the second bracket, which is when 1 minus x is equal to 0, which is when 1 is equal to x. And that's going to allow me to make my sign chart. My sign chart is going to be, a little bit simpler than some of the ones we've done because there's only one critical number. There's only when x is 1. So we're going to have an interval from negative infinity to 1 and the interval from 1 to positive infinity. The only factors we have. Now, I know we don't need to include it, but I'm going to throw it in there just for consistency. I'm going to put e to the negative x in there, but before I do anything else, I know that's always positive. E to the negative x is never negative, and I would encourage you to maybe take a look back at 30-1 for those exponential functions. The other factor, though, is 1 minus x, and then because we are using this notation, I'm going to put y prime down there. All right, 1 minus x. So 0 is within negative infinity to positive 1. What's 1 minus 0? Positive or negative? Well, it's positive. So y prime is positive at that point, or sorry, at that interval, over that interval is a better way of saying that. From 1 to infinity, let's say 45, 1 minus 45 is a negative, therefore y prime is a negative. Now what this means is that the function is always increasing until this point right here, which is when x is equal to 1, and then it's always decreasing. Now, you might not remember this, but back in chapter 5, we talked about if there's only one place where the function changes from increasing or decreasing, that becomes our absolute in that case. So I'm going to say that this has an absolute max, and I'm going to put at x equals 1, and then I'm going to put maybe below it, there is no absolute min. We'll take a look at this graph in a second as well. So if the absolute max is at x equals 1, I'm just going to track up a little bit. We have a function. We know that y is equal to x times e to the negative x. That means that y is equal to 1 times e to the negative 1. So y is equal to 1 over e. So our absolute max, if you put the decimal there, it's not the end of the world, but 1 over e is our exact form. Our absolute max is going to be at 1 comma 1 over e. Now again, if you did plug that into your calculator, it would give you that decimal. I would rather see 1 over e, because it shows that you know how to find the exact form of this. And just to give you an idea of what this graph looks like, never a bad idea to confirm what we've done graphically. I'm just going to pull up Desmos here, and we will take a look at the graph of y equals x times e to the power of negative x, and I get this weird graph. Now, there's the max right there, 1 comma 0.368. 0.368 is 1 divided by e. I like showing this because I hope illustrates that Desmos is not better than you, right? You can do this better than Desmos can because we can find the exact value. And then what we see, I hope pretty clearly, this graph cannot have an absolute min because it does go down to negative infinity. The graph is increasing until this point, at which case it is neither increasing nor decreasing. Y prime is equal to 0, and then y prime would be negative for the rest. Does have a horizontal asymptote, and it does have a vertical asymptote, but that doesn't particularly matter for this question. All right, one left to do. And it's a nice kind of, okay, what is the point of this? It's not just about doing exponential functions. It's about adding the ability to deal with another type of function. We still have to be able to do tangent lines, increase, decrease, concavity, maxes, minimums, and we're not going to give you a lot of them, but curve sketching is really on the table here as well. So it wants us to find the equation of the tangent line to this curve at the point negative 1 comma 1. Well, we have the point then all I need, I'm going to write, I need the slope at x equals negative 1, which means I need dy over dx when x is equal to negative 1. That's that calculus connection, that if we have a point and a slope, we have a linear equation, we just need to make sure we understand how to get there with the calculus. Now, in order to get dy over dx, and I want to write this at least once in this section, I am going to take the operation, the derivative with respect to x of both sides. And I know that, you can skip this when you show your work. There's nothing wrong with that. But I really think it's important that this statement is how we get dy over dx. We apply a mathematical operation, the derivative, on both sides of an equation. Now, technically this is implicit differentiation, but it's pretty simple because d over dx of y is 1 times dy over dx. The right-hand side, we have a bit of a product rule. So x e to the x is going to be 1 times e to the x plus x times e to the x plus the derivative of e to the x, which is e to the x. And I know we don't need it, but I am going to write a 0 in there. And what I'm going to do is I'm just going to try to show you where the derivatives have went. This entire section in red is the derivative of x times e to the x. E to the x is the derivative of e to the x, and 0 is the derivative of 1. Just to try to make that as clear as possible. We could clean this up. And I think I want to, at least once, just to make sure we see how factoring works with these exponential functions. I'm going to write that dy over dx is equal to, I'm going to factor e to the x out, which leaves me with 1 plus x plus 1, which means my derivative can be written as e to the x times 2 plus x. There's not a huge benefit of doing that in this question, but I think it does, sharpen again those factoring skills. All right, that's dy over dx. So dy over dx when x is equal to 1 is e to the power of 1 times 2 plus 1, which is 3 times e to the power of 1, or because the default exponent is 1, you can write that as 3e. Okay, and I made a mistake. Was I really supposed to put 1 in for x? I don't know how I did that right below where I wrote it. So we're going to quickly modify that so I'm not giving you guys the wrong notes. We don't want dy over dx when x is 1. We want it when x is negative 1. Sorry about that, team. So when I put negative 1 in for x, we'll do it right this time, I promise. I get e to the power of negative 1 times 2 plus negative 1, which is e to the negative 1 times 1, which is 1 over e. Now, we have our slope. We have our point. We're now going to use point slope form for this. This is really where point slope form starts to shine. I'm going to try to avoid making a mistake again. So I'm going to write this down for myself, that the point is negative 1 comma 1, and the slope of that tangent line is going to be 1 over e. Not sure why there's a bracket there, but that's okay. So the equation of the tangent line is going to be y minus 1 is equal to the slope 1 over e times x minus negative 1, which is maybe a little bit better or easier to write as y minus 1 is equal to 1 over e times x plus 1. You certainly could manipulate this for b. You do not need to do that. That is an equation of a linear. It's just not in, general form or y equals mx plus b form, and that's fine. I said that, and this is the last example, so we're going to do it really quickly. This would be y is equal to 1 over e x plus 1 over e plus 1. And I'll write that a little bit bigger, that this would be our slope-intercept form. And it's a little bit tough to see. I'll write it underneath that in our slope-intercept form, 1 over e is m, which is the slope, but then this entire expression is our y-intercept. Not particularly important, but what is very, very important about this section is the ability to take the derivative of e to the power of x. We are going to look at different bases as we go forward, but to really, really get into that, we're going to need to use the logarithm. And so we're going to talk a little bit more about logarithms in 8.3. So here's the full assignment. Good luck with this. This takes a little bit of practice, takes a little bit of work. And if you are struggling with, not so much in this lesson, but using the logarithm or dealing with exponential functions, please do take a look at my YouTube channel and look at Chapter 7, which is exponentials for Math 30-1, and Chapter 8, which is logarithms for Math 30-1.